So in this week's experiment, we're going to be studying acceleration. Now you can't trust your finger to constantly accelerate something, you're just not that accurate. So instead we're going to trust this fan to do it for us. So when I turn on the fan, it's going to cause the cart to accelerate down the length of the track. So let me show you that. Now we're going to study 4 different cases using this fan cart, but before you start taking any data, as always, what you should do is first level your track. So you take this spirit level, which is just a plastic tube with a bubble inside it. So you orient the spirit level so that it's parallel to the length of your track, and you check whether that bubble is right between the lines as accurately as possible. If it's not, then you come over to this end of the track, and this end of the track rests on a screw. You could twist that to raise and lower this end of the track and make things as level as possible before you start taking data. And then you would put this guy back on the track and you're ready to begin. So in question 1, the motion that you're going to be studying is you're going to start this at the edge of the dead zone, so our effective origin, and you'll start your program running. I'll show you the program in a moment. Start the fan going, and then you let it accelerate from rest freely down the track. So you're starting from rest. Now question 1a says if the fan cart starts at rest at the origin and accelerates to the right, that is in the positive direction relative to the sensor, describe how the position and the velocity of the cart will change. So question A is asking you about what the cart will do. Question B is going to ask you what the graphs do, so what the graphs theoretically will look like. So try not to get those mixed up. So as I just said, question B is where you are expected to make predictions on what your velocity time graph and your position time graphs are going to look like. So this is constant acceleration. A position time graph will always show acceleration to be a curved line. A velocity time graph, if it's constant acceleration, should show a straight line. So you make your predictions and sketch them into your lab manual. Then, question C, you're actually going to study this motion. So you'll start your program running and start the fan cart going, let it accelerate down the track from rest, starting at the edge of the dead zone. You capture that on screen, you paste it into your book. You will need to fit a straight line to your velocity time graph, but I'm going to show you how to do that in a moment. And then in question D, they tell you to comment on the similarities and differences between what you predicted, so what you sketched in your manual, and the graphs that you actually got off the screen. Now, I'll warn you that to get full marks for this, you do need to talk about similarities and differences. The differences might be something like the bumps and wiggles that you see on the real-world graph versus the ideal world case that you sketched in your predictions. When you talk about the similarities, however, you need to be a little bit careful. It's never enough to say my predicted graph and my measured graph looks the same. You have to be specific about how they are the same. I suggest that you use graphing language to do this. So for example, both of my graphs were linear. They both had positive slope. They both had negative slope. They both had zero slope. The y-intercept was at 0. The y-intercept was above 0. I saw curvature upward or downward. So use graphing language to talk about how your graphs, your predicted graphs, and the graphs you got off the computer screen, how they are similar. So now, before I show you the next 3 cases, I'm going to demonstrate how you use the program that we're using this week. The program is called Acceleration. So as usual, all the files you need are in this 1100 folder. So double click that and open it up. Last week we used velocity. This week we're going to use the acceleration program. So double click on that and let it open up. And once it does, the first thing you notice is there's 2 graphs. There's a position time graph and there's also a velocity time graph. Now we're studying acceleration this week. We've got a fan that's going to accelerate the cart down the track. So on a position time graph, we expect acceleration, constant acceleration, to look like a curved line. On a velocity time graph, we expect constant acceleration to look like a straight line. So I'm going to demonstrate this, and it's going to get a little noisy for a second, so bear with me as I have to press this start button over here, and then I'll turn on the fan and let it accelerate the cart down the track. So one moment, please. Okay, so as expected, the position time graph is a curved line. And the velocity time graph, except for a little bit of jaggedy data here, is basically a straight line. So we're going to actually fit a straight line, get a slope value for this. But before I do that, I actually want to stretch this graph out a little bit so that it's easier to read. So first thing I do is click on that graph to make sure it's the one highlighted, and then I go Display, Settings, and you start on the wrong tab to begin with. So you want to go over to Axis Settings tab, and then down here in Extras, I want you to unclick Lock Origin Position and Lock Scaling. Turn these two guys off. Hit OK. So now, when I hover my mouse over the line, and I can grab the whole thing and move the origin down. So I want to move it, say, to there. I also want to stretch this upwards so I can see this linear section a little better. So if I move the mouse over farther so it's hovering over one of the numbers, and I can click and drag to stretch the axis out. So get the graph looking nice, and I want to fit a straight line to a linear section of this graph. So it's not totally linear, and that's pretty normal. You want to just choose a section that does look fairly linear to you. So I'm going to say that bit there looks pretty linear. So I'm going to fit a straight line to it, and the way in which I do that is there's this little button here that says Fit. Press that and select Linear Fit. And it fits a straight line through my data that I selected, and it gives me the slope value. I have to figure out what the units are, but they give me the units on the axis. It shouldn't be hard. And this is the graph I'm going to print out. So the manual actually says produce a position time and a velocity time graph. In other words, print both of these guys out. I'll just tell you that the second one is the only one we need. So this guy here is the one we want to print.
So that means that if you're doing the paperless lab report system, you're going to screen capture just this second graph, and then that's what gets pasted into your electronic lab report.
So now I'm going to tell you about the next three cases that we study using the fan cart. In all of these cases, what you see in the manual is going to look exactly the same as what you saw for part 1. So question A will ask you, how does the cart move? Question B asks you to make predictions about what the graphs on the screen are going to look like. Question C is where you actually capture the motion on the screen. So you take graphs, and you would fit a straight line through your velocity time graph, print these off, and then paste them into your book in part C. And then part D asks you to talk about the similarities and differences between what you captured off the screen and what you predicted you would see in part B. So question 2, the motion that we're going to study is that the fan cart is going to have an initial velocity. Well, how do we actually arrange that? What we do is, in the last question, you started at the edge of the dead zone and you started from rest, and you just let the fan cart accelerate from rest away down the track. In order to have an initial velocity when we start taking data officially, all we're going to do is we're going to move this guy right into the dead zone. And then when the cart actually leaves the dead zone, it will already have an initial velocity. So just to demonstrate, if I start this right in the dead zone, when it left the dead zone, it already had a velocity. So that was the motion we wanted to capture. So that's how you do question 2, is just start in the dead zone, and then you'll have an initial velocity by the time you leave the dead zone. The motion that you're going to study in question 3 is slightly difficult to get, so hopefully I'm talented enough to show you this. What you do is you start at the far end of the track, and you'll start the fan cart going, but you'll push it towards the sensor, and then the fan is going to slow down the cart and turn it around, and it'll head towards the end of the track again. So I'll try and demonstrate this for you. It's a little tricky. So that's the sort of motion that you want to capture, is it heads this way initially, and then the fan itself will stop the cart, slow it down, turn it around, and it'll head towards the end of the track again. Now there's one subtlety of the data that you may see here, so I'm just going to pause the video and show you what you may see. This would be a change in the acceleration based on the direction of travel. Theoretically, this is not supposed to happen, but with our equipment, it is quite common that some groups do see it. So as I said, I'm just going to pause the video and show you that now, and then I'll come back and show you the 4th case. Okay, so this is, spoiler alert, what your 3rd case is going to roughly look like, but not necessarily exactly. The reason I'm pointing this out to you is we expect to see a straight line when we've got constant acceleration. And of course, we've got one fan giving us the acceleration for the whole experiment. We don't expect that fan's strength to suddenly change. So there's no reason why this wouldn't be a perfectly straight line. And it's entirely possible that for your equipment, it is a perfectly straight line. But it's also pretty common to see that you have two sections that have slightly different slopes. So what I mean is I've highlighted this section here when the velocity was in the negative direction. So that was just after I pushed it towards the sensor. And if I put a fit on that, there's my slope when it was going negative. Up here is the slope when it was going the positive direction. So after it had turned around, it was heading away from the sensor again. And you can see that the line here doesn't match this line here, that I have slightly different slopes when it was going towards the sensor compared to going away from the sensor. So I call this the kink, as you may or may not have this kink in your data. It depends on your equipment. So if you see the kink, highlight the other section as well and print out two graphs. So you'll have one graph that shows the fit to this part when it was going in the positive direction, and a second graph that shows this fit when it's going in the negative direction. Print them both out, because the last question of the experiment says, did you notice any difference in the acceleration magnitude related to the direction of motion? That's what they're fishing for, is they're talking about this. Did you see a kink in your data or not? In an ideal world, you would not. So this is a real world effect. What's going on? If you see this, print out the two graphs and try and explain what's going on. What could cause the acceleration in one direction to be different than the acceleration in the other direction, given that we did not change the fan? Now, in case 4, what you're going to do is you'll start the cart at this end of the track again, but you're going to turn it around so that it's accelerating towards the sensor. So please be careful to catch it before it actually crashes into the sensor. But you would start it from rest down here and it would accelerate towards the sensor. And that would be the motion that you would capture. So when you get to question 5, that is, you've finished the 4 cases that you study with the cart on the track, there's some questions here that some students find a little bit tricky. So I'm going to give you some hints here. Not the answers, but just some hints. So question 5 is, describe a real-world situation where the acceleration is either in the same direction as the direction of motion, or the acceleration is in the opposite direction to the direction of motion. So with the cart on the track, we studied both of these. We had cases where the acceleration and the velocity were both headed in the same direction. And that third case, to begin with at least, we had the acceleration being in the positive direction, but the initial velocity being in the negative direction. So you looked at these. So now you just need to think of real-world situations where that similar state of affairs exists. So think about throwing a ball in the air or stuff like that. Second question, or pardon me, the 6th question says, using the apparatus provided, so the same cart, fan, and track that we had, how could you get an acceleration that was larger than what we measured, or an acceleration that was smaller than what we measured? So think about how you could tweak the track, for example, to make the acceleration larger or smaller, or the cart itself, or the fan itself. So you're allowed to play around with any of those 3 things, and there's more than one answer for how you can do this. Question 7 says, describe a real-world situation where an object has a large acceleration but a small velocity, or a small acceleration but a large velocity. So think about things like a rocket ship taking off, or a car coasting on the highway. Try and think of a situation where the acceleration might be huge but the velocity isn't very big yet. Or you have a small acceleration but it's actually going really fast too. So just try and think of something like that. Question 8 says, using your data and your fit lines, find a value for the acceleration for the 4 cases that we studied. By the time you get here, you've already got these numbers. You should not need to do any calculations. You should be able to just write down the numbers. Questions 9 and 10 are sort of related. Why are the first 3 measured accelerations listed all positive, and which acceleration magnitudes roughly agree with each other? Can't give you an answer for this, but what I will say is the thing to remember when you're trying to answer this is that we only had one fan. So all of our accelerations came from that one device. So if you keep that in mind, it becomes a little easier to answer these questions. And the last question, Did you notice any difference in the acceleration magnitude related to the direction of motion? As I hinted earlier, that has to do with that third case where the cart changed direction. Did you see a kink in the data, and if so, what could have caused that?